Hello, class. I'm not sure actually if we're going to be doing this in person or if we're going to be doing it by online instruction. So I thought that I would do a first lecture for this course in online instruction, since I have no idea what the situation is going to be like May 5th. So let's start this. I really wanted to do this lecture anyway, just for posterity, to talk about Maxwell's equations and the introduction to electromagnetic field theory. And electromagnetic field theory is a great course and really lets you know a lot about what's going on. It also is can be mathematically intensive, and even the concepts obviously are very intensive concepts. Now, what I want to start off with today is not the easiest concept, but I want to work through what the most important result of Maxwell's equations are. And throughout your life as an electrical engineer, you're going to hear people refer to Maxwell's equations, Maxwell's equations, Maxwell's equations. Well, the outcome of Maxwell's equations is really realizing that mathematically we could determine what the speed of light was, and that the speed of light, we didn't know this at the time, was actually an electromagnetic wave, right? That when we started to look at electromagnetic waves, and we created, electricity, and then all of a sudden we started to make it into waves, AC circuit theory, and we started to see how things work between magnetic and electric fields. And it was only then, and you might have said that Faraday had some ideas about it, but didn't have the mathematical rigor to put those ideas into a mathematical framework. Whereas James Clerk Maxwell, although he died at a young age, really did understand the mathematics necessary, and was probably one of the few people in the world at the time that really understood that. But what he did, as he was playing around with all of the numbers and applying the mathematical operators to them, is he realized that, oh my God, this thing we call light, and in fact, he realized very quickly that light was an electromagnetic wave, similar to how radio was an electromagnetic wave, similar to, just minor things, putting a magnet and having a wire run current over the top of it, all electromagnetic waves. And so, and there were some things, some of the laws that he realized. Now, when we say Maxwell's equations, we're not really talking about equations that entirely Maxwell came up with himself. In fact, the first equation in there is Gauss's equation. And so, and there's Ampere's law. And there's a bunch of these different laws, and just similar to Einstein, how Einstein brought all of these various different laws together to eventually have the revelation that special relativity gave us, right? That nothing can move faster than the speed of light if we're observing it, because we're observing it via light. Right? I mean, isn't that how we see things? We see it via light. So how does anything go faster than the speed of light? And we've talked about that and other, how it pertains. And Maxwell did very much the same thing. I'm going to just write down a couple things. If we look at Maxwell's equations, we can see that Maxwell's equations in the differential form are the del operator dotted with the electric field. And if I dot the del operator with the electric field, that equals the charge divided by the permittivity of free space. And again, I'm going to go back and discuss all of these. In fact, even that first one that we put up there, what is the del operator, right? Well, the del operator basically says that the partial derivative of x, of whatever the function is that this is going to be dotted or crossed into, that the first thing is the change in whatever the quantity is with respect to x, and that's in the x direction or the I hat direction. And I guess we're going to have to go back to some cross products, but I'm pretty sure that you've gotten cross products. You may have even gotten them from me when we were working with cross products in engineering mechanics. I'm not sure, but anyway, the del operator is the partial derivative of x of the function, whatever that function is, right? And that function could be a function of multi-variables. Right? Maybe it's a function of x, y, z, and t, but this would just be the partial differentiation with respect to x, and that would be in the I or the x direction, right? I hat happens to be a unit vector in the x direction. So that plus, and you can probably guess what the next one is, d to dy in the j direction or the y direction, and then plus of dz in the k hat or z direction, right? So that's what the del operator is. And we'll refer back to that a little bit as I work through this lecture on, what Maxwell's equations really do and how they proved to James Clerk Maxwell. That's what this lecture really is about. They proved to James Clerk Maxwell that light is, not only that light is an electromagnetic wave, but that we can also find the velocity of all electromagnetic waves, but light included in that. All right, so that's one of Maxwell's equations. And the second Maxwell's equation is that del, the del operator crossed with the electric field, is going to be equal to the minus the change in the magnetic field that's created per unit time. Okay? So that's the second of Maxwell's equations. I'm sort of dumbing these down, by the way. There's more, in some of these equations, there's more. In some, we could almost do it with less. Let's do the third equation, though, and that's the equation that says that the del operator dotted with B is going to be equal to 0. And again, I'm going to go through conceptually all four of these equations. Now, I'm also going to write the fourth equation here in its simplest form for what we're doing today, and that would be that the del operator crossed with my magnetic field vector is going to be equal to the permeability of free space times the permittivity of free space. Now, I say the permittivity of free space, but it really depends on the material that this is occurring in, because then we would be looking at the permeability of that material. Right now, I'm saying that we're just, doing this in air. So the permeability of air is very close to the permeability of free space, and so I'm just writing those down. Times the change in the electric field vector with time. Now, you're probably saying, well, and that's the fourth equation. Now, there's actually another part on there, and I'll explain that other part when we're talking about it in the lectures dealing with each and every one of the four equations involved in Maxwell's equation. But I'm just going to use it in this form right now. There are a couple things that we want to know. right? And that is how exactly does a um, electromagnetic wave propagate? And so the way I want to show you this is I'm going to draw a vector field here, right? And I'm going to do it on a Cartesian coordinate system where that's the y-axis. I'm going to draw this in sort of a, and this is my x-axis, and then this would be my z-axis. And we're going to look at the propagation of a wave. So if I was to look at a wave here, I would see that along this line, let's say, I would see that the line would be something like that, right? And then we really have, I'm just going to, for each and every point along that line, I just want to point out that, you know, we have a vector for that individual point. And this wave is moving in the x direction. I probably should have made that a little bit further. This wave is moving along in the x direction. Now, perpendicular, and you can see that if this is the E field, that this, at each point on here, you can see it's changing, right? And it's moving at the same time. So the electric field is going to be a function of x and t. Right now you can see that this point is way up here, but what if this wave is going to continually move along? Well, then this point is going to, if I looked at that point a second later, or some interval of time later, that would be this point, wouldn't it? Because this point here would have moved up to that point, and this point would have moved up to that point. So the electric field that is in the y direction and propagating along the x-axis is really a function of x and time. Now, what we know is that when the electric field reaches a maximum in an electromagnetic wave, that also the magnetic field reaches a maximum too. And we can draw the magnetic field perpendicular to the electric field, right? And it's a wave, and both of them together are propagating in the x direction. This whole wave is propagating in that direction, right? And of course, this would just continue on. There would be another one here, you know, as we go on, because it's just a continuous waveform. And that waveform propagates in that direction. Let's call B then. B is going to be a function of x and t2, right? Because B is also along the x-axis. And if I looked at this point right here, right at this instant, well, I've got the magnitude, but didn't I say that this wave is propagating along there? So in this point right here is going to be in this point right here in just a second. And then that, instead of this being a maxima, it'll be a minima. So at each point along that line, we're going to have E and B perpendicular to each other, traveling. Now, in the y direction, we call that j hat, right? Because a unit vector along the j direction is going, the y direction is going to be j hat. A unit vector along the z direction is called k hat, and a unit vector along the x direction is called I hat. Okay? And again, that's just review. You all should have gotten that in engineering mechanics. If you took engineering mechanics from me, you know your cross products and your dot products and everything with no problem. And so I'm hopeful that everybody in class did take it from me. So now, we've got two different perpendicular things here that make up our electromagnetic wave that is propagating in the I direction. How do we know that it's propagating in the I direction? Because E cross B equals velocity, right? So let's just do that. Well, E we can see is in the J hat direction, right? And then B is in the K hat direction. J cross K equals I hat. Let's just draw our little circle here. J, K, I, right? So if we go in the direction, and I did not create this, by the way. Beer and Johnston are the ones that I think created this originally, but let's just look at this. J cross K equals I. K cross I equals J. I cross J equals K. As long as we're going around in the correct direction, it's always going to be a positive. So J cross K equals I, and what do you know? That's right. This is propagating in that direction, as you can see. Now, I also, when I'm doing this lecture, I want to bring out another equation, an equation that you probably have seen in your partial differential or your differential equations course. And that is that 1 divided by v squared times d, the partial derivative of y, the second partial derivative of y with respect to t. And notice I've got d squared y over dt squared. That's how we write it, right? And that equals the second derivative of y with respect to x, right? That equation is called the velocity equation in differential equations. And you're probably thinking, well, that says something about the velocity of a waveform. And that's right. That's exactly what it says. It says something about the velocity of a waveform. Now, let's see what was going on inside Maxwell's brain. And I don't know if that's that easy because he was quite a complicated fellow. But let's look at our equations that we have over here. These 4 equations that we're calling Maxwell's equations, and see how those are going to help us figure out that this is an electromagnetic waveform and that it follows all of these, of course, but that it also proves beyond a shadow of a doubt that light is an electromagnetic waveform. Just like radar, just like microwaves, just like gamma rays are all electromagnetic waveforms, so is light. And this is what Maxwell did. He said, okay, well, how can I write the electric field? Let's see. The electric field is only changing in the y direction, right? And so it's really planar to the y-x plane. It's in the y-x plane. So how could I write that? Well, is there anything moving in the I direction? No, these things are all going up and down in the J direction. So it would be 0 I hat plus my electric field, right, is all in the J direction. So my electric field, which is a function of X and T, because like I say, this is moving down here. We're always looking at that one point right there. And that point one that right there might have, at one instant in time, might be a maximum. At another instant in time, might be a minimum. At another instant in time, might be down here, might be halfway to maximum, right? Because this is propagating along that thing, and we're just looking at these individual points and seeing how they're changing. Now, these are changing not only with time because the waveform is propagating down there, but they're also changing with distance along the x, right? Because you can see that this is going to be a maximum, but this right here is going to be half of a maximum. So it changes both with time and both because it's a sinusoidally varying wave that's propagating down the x-axis. It's changing with x and it's changing with time. And of course, that is the J component of the vector. And, you know, I shouldn't put the vector on top of that. Why did I do that? That's just the magnitude of the electric field function. All right. And then how about in the k direction? Well, are any of these things going in the k direction out this way? No, only the magnetic field is going in the k direction. This is going in the y direction or the j direction, and this one is going in the z or k hat direction, right? And so in that direction, we've got 0, 2. So 0 k hat. So that's how I would write the electric field that I've got here. And you're probably saying, well, you know, the magnetic field is pretty much exactly the same as the electric field, but instead of going in the y direction, it's going in the z direction, isn't it? So I could also write my magnetic field. My magnetic field is not going in the I direction. My magnetic field is not going in the J direction. My magnetic field is going in, and of course my magnetic field, the same as the electric field, is a function both of where it is on the line and at what time it's on the line. Now, if this thing was just staying here and it wasn't moving at all, then it really wouldn't, this thing would just be a function of x, wouldn't it? But no, this is actually propagating down here. So each one of these little individual spots on the x-axis is going to have both a magnetic and an electric field that are constantly changing. So it would be bx of t in the k hat direction. So that's how I would write both of those two vectors that I've, or functions that I've got here. And of course, vectors too, because we're working in 3 dimensions, aren't we? Let's also not forget what our del operator is, because if you look, the del operator is used in all 4 of these equations, isn't it? That's right. So the del operator is used in all 4 of those equations. Let's look at one of those equations. I'm going to look at equation 2 first off. Equation 2 tells us that the del operator crossed with the electric field, and we've got those both in vector form, don't we? We've got this in vector form, and we've got this in vector form, so we can easily cross multiply those 2 things. Now, that's going to equal minus the change in the magnetic field with the change in time. So we should be able to do that too, to take the derivative of that. So let's look at del cross E first. Well, we know this is del and we know this is E. So let's just do it. So del cross E. So the change with respect to X in the I direction crossed with 0I. Well, you can't cross anything with itself, can you? So we know that's 0. How about the change in Y for 0, the change in Y, or I should say J cross I is obviously going to be 0 because that's 0, right? And how about K? Well, this is going to be the change in Z with K crossed with I gives me J. That's all fine, except this is 0. So that's going to be 0. So all of those along there are 0. This d of x, I can't do that. And then J crossed with I, we can't do that. K crossed with I, well, you can't do that either. Let's do the del operator crossed with this. So I've got I crossed with J, right? We're doing del cross E. Yeah, let's not forget what we're doing. Del cross E. Not E cross del. We're doing del cross E. All right. So let's take the second one, and this is going to be the change in, the change in X for I crossed with J. So let's do that. I crossed with J gives me K. And now can we do this? The change in E with respect to X, is X actually a variable there? Yes, it is. It's a variable there. So I crossed with J, that gives me K, right? I crossed with J gives me K. And then the change in whatever with respect to X times E. So the change in E as a function of X and T over the change in X. And that's in the K direction, right? Now, let's keep going and just see what else we've got here. So now, how about the change in Y times J? Well, J crossed with J, we can't do that, but we can do the last one. The change with respect to Z in the K direction crossed with this. Well, you know, there is no change in there, is there? There's no change with respect to Z in there. So that also would be 0. And then let's do the last one, the 0K. Well, the change with respect to 0 with X, nope, that doesn't work. The change with respect to Y of 0, well, that doesn't work either. So all of those fall out. The only thing that we really have here is the change in the electric field with the change in X, and that is going to be in the K direction, right? So I think everybody can see that and all of that's going to be equal to minus the change in B over the change in E. Now, I want to look at another one of the equations, and I'm going to look at number 4. So let me circle this one because we're going to come back to this equation. I just put the 2 here because that is number 2 in there. Now, let's look at number 4. That equation is the same thing, the del operator crossed, but this time with the magnetic field vector. And that equals mu sub 0 times epsilon sub 0 times the change in the electric field with the change in time. Okay. Yes. So del cross B, let's do that. Well, you know, we're really doing it pretty much the same lines, and I think everybody can see sort of what's going to happen here is that when I do del cross B, the first thing we'll do, let's just look at B over here, is that I've got I, can't do I with that, right? And then you've got J, can't J crossed with I, that's great, but we've got a 0, so that's going to be 0. And then K crossed with I, well, that gives me J, but it's also 0. So we don't have anything with Z there. So let's do the next one. So del crossed with this, I've got the change in, again, it's going to be the same, isn't it? Because I've got the change in that with respect to X, well, there is none. Change in that with respect to Y, well, there is none, then J cross J doesn't work. And then change with respect to Z, well, there is none, it's just 0. So that's not going to work either. So let's look at the last one that I've got here. Well, that's going to be looking at the change in X. Yes, we can do that. And then I crossed with K. I crossed with K is going in the opposite direction. So instead of that being a positive J, since it's going in the opposite direction to the arrow, it's going to be a negative J, isn't it? So when we look at del crossed with B, The last one we're doing, del with respect to x, I crossed with b, so I've got the change of b as a function of x and t taken with respect to x. So that's the derivative, the partial derivative of b as a function of x and t taken taken to the derivative of x, or you know, derivative with respect to x. And then let's do the cross multiplication too. I've got I crossed with k. Now I crossed with k gives me minus j. So I'm going to put the minus out here, and I'm going to put the j right there. Okay? Now let's do the next two. I don't want to just leave those off. Now the change in b with respect to y, well, you can see that there is no y. So I can't take the derivative with respect to y because it's not a function of y. So that would take care of that, and then k cross k equals 0. So this is what I get when I look right there. And in fact, this right here is what I get when I look at this. So that's the one side. And we know that the other side of this is going to be equal to mu sub 0 epsilon sub 0 times the change in the electric field with the change in time. And you know, we should say the change in electric field, and that electric field is a function of x and t. I don't want to write that all the time, but you know, in this case, we can. So we've got a minus there and all of those. We can we now know that those two are equivalent too, right? So what I want to do is I want to take this equation right here, that first equation that we used. Let's call that equation A, now that we've got it all done. I want to take equation A, and I want to take the derivative of it with respect to x. Just a second, let me just bring that in there. I want to take the derivative of this with respect to x. So let's do that to both sides. So I know that if I've got the derivative with respect to x of the derivative of e as a function of x and t with respect to x, right? That's going to be the second derivative of e. I'm going to do this, but I also, if I do that, I've got to do the same to the other side, don't I? So I've got minus dB over dt, so I've got to take that with respect to x too. And so if I take minus the change of the magnetic field with respect to time and take that with respect to x, this is what I get, right? So now let's make an equivalent to that. I want you to see this, and if you don't know this and haven't gotten this out of your partial derivatives class, I don't know why you haven't. But let's just switch around the denominators here, shall we? So this is going to be the change in with respect to t of minus dB dx. Now you're probably saying, can you do that? Can you actually do that? Yes, of course you can, and God, doesn't that make life easier, right? And so that's what I've done. I've looked at this now with the change with respect to time of minus dB. And of course, dB, let's not forget, dB is a function of x and time, right? So we've got that all laid out like that. Now, let's take the second derivative of this, right? So the second derivative of this is going to be d, and remember d or e is the derivative of e with respect to x, the second derivative of e with respect to x. So that's what we've got right now. we've got this equation right here. Let's just look at that equation for a second. All right. Now, where have we seen something like that before? dB minus dB divided by x, or with respect to x. Oh my God, here it is, minus the change in the magnetic field with respect to x, don't we? And we know that that equals this. Actually, the negative of that equals this. So I could write that. I could, since this is a negative right here, I could just put that in for it, couldn't I? Right? So that's a negative already. And this is a negative with respect to x. So negative with respect to x, negative with respect to x. So let's just put that in there and equate it to this. So I'm just going to do that down here. So the change in unit time of, and let's replace that with what we've got on that side, the absolute permeability times absolute permittivity times the change in my electric field as a function, which is a function of x and t with t. So that's all I've done. I've just basically replaced this right here with this. And then I'm still going to say that this is the same as the second derivative of E as a function of x and t with x. You know, let's extend this all the way through here now. So what that gives us is that gives us mu sub 0, epsilon sub 0, and then the change, the second derivative of the electric field as a function of x and t with t, right? Oh, I'm sorry, squared. What was I thinking? And then we've got that over here. You know, we have an equation. I'm just going to put a star next to that equation. That equation right there, d squared y, the second derivative of y with respect to t, and the second derivative of y with respect to x. You know, I've got the second derivative of e with respect to x here, don't I? And wouldn't that be equivalent to this thing right here? The second derivative of y with respect to x, the second derivative of e with respect to x. That's on one side of the equation of the equal sign. And then on the other side of the equal sign, I've got that same function, e of x and t, but taken as the second derivative of time, times this. Now, if this corresponds to this, and this corresponds to this, then this must correspond to that. And so we can say 1 over velocity squared has to equal mu sub 0 times epsilon sub 0. And this is where Maxwell got. Maxwell got to this point, and he was thinking, God, can this be right? Can this actually be right? And what he then found was he's saying, well, you know, what is this strange velocity I'm getting here? If I take 1 over the square root of mu sub 0 and epsilon sub 0, what do I actually get? And what I actually get is a velocity of 300 times 10 to the 6 meters per second. Right? Now, when Maxwell saw this, he thought that cannot be a coincidence. That cannot be a coincidence, because he knew that what the speed of light was. We knew the speed of light was very close to this. It actually wasn't quite calculated at that, but it was so close that he thought, well, you know, is this possible that with these equations that I've taken from other people, I've actually figured out that light is an electromagnetic phenomena, just like microwaves and everything else. He was doing this at a very, very low frequency. And he was just working with magnetism and electricity. He didn't realize that these things would be self-propagating. You know, if you think about light, it's the first perpetual motion machine, isn't it? And it's not even a perpetual motion machine, but it's pretty darn close. So that's what we ended up getting. And of course, that V equals the speed of light. And that's really the most revolutionary and important fact that you can take away from Maxwell's equations, is that they finally brought us an idea, and not so long ago, you know, 100, 150 years ago, that light was actually an electromagnetic wave. Okay, I'm going to stop it there, and I'm going to see if I can actually put this